Here on this page, I have summarized all the information needed for analyzing thermodynamic processes. This can be an overwhelming amount of information, but especially the table here on the key concept slide can be very useful to write in some notes somewhere or have access to. There's definitely problems we look at in this course where using some of the formulas that are listed in this table are going to be useful for finding an answer. And I've organized the table according to columns corresponding to the amount of work done by a system of an ideal gas in one of the four types of thermodynamic processes. And then the other column is the formula for the heat in that type of a process. Now, necessary information for this table includes the monatomic heat capacity and the diatomic heat capacity expressions. And at the top here, I've written the first law of thermodynamics in terms of heat capacity. So usually we see Q is equal to delta E plus W, but if the delta E, which is the change in internal energy, represents the change in the thermal energy, then that is equal to the heat capacity of the system times the change in temperature. Now, in the case of a gas, in order for this to hold true, since gases expand and contract relatively easily, we have to restrict our attention to the constant volume heat capacity. One way of thinking about that is to say, well, when we introduced heat capacity and specific heat earlier, we were thinking about solid substances, for which it wasn't really an issue to think about it expanding, even though we know they do a little bit, but it's relatively small compared to what a gas might do. So in order to kind of make things work, we need to think about constant volume heat capacity. And I've got some stuff here on the whiteboard that might help us understand that. So for one thing, recall that the definition of heat capacity, that's a thing that in the past I've used the capital letter C to symbolize. Sometimes it's hard to tell unless you see them next to each other, maybe what's a lowercase c versus an uppercase capital C, but this is meant to be an uppercase capital C for heat capacity. And the definition was that it's equal to the ratio of heat to temperature change. Now, one of the reasons to say that we're looking at constant volume is because that means that the work done by the system is going to be equal to zero. And then the first law of thermodynamics states that the heat applied to the system is equal to the internal change of the energy, the change in the internal energy of the system, which in this case is going to be thought of as the change in the thermal energy stored in the system, which we're saying is therefore equal to the constant volume heat capacity of the system where it's a gas. And so this, in that sense, this line right here, I think, relates the original definition of heat capacity to some results that we got for the thermal energy of both monatomic and diatomic gases. So that's what's done in kind of these next two sections here, is that for a monatomic gas, the thermal energy was equal to 3/2 nRT, where I've taken here on the whiteboard, I've used the molar expressions rather than the kind of molecular level expression. So I'm using N as the number of moles and R as the ideal gas constant rather than the Boltzmann constant. T, of course, is still going to be in kelvins. But if this formula holds true, the way we presented it with the kinetic theory of gases, then a change in thermal energy of that gas would be equal to 3/2 nR delta T. And based on the fact that at constant volume we've related delta E sub T to the heat, which again then reconciles with the original definition of heat capacity, we can therefore say that the constant volume heat capacity of a monatomic gas must be 3/2 nR, which is this formula right here on the key concept slide. It also appears here again as the molecular version. Diatomic works very similar, but what we saw when we explored the equipartition theorem is that there are those two additional internal rotational degrees of freedom that add to the amount of thermal energy at a given temperature for a given number of moles of an ideal gas compared to what it would have been if it had been a monatomic gas. So that's hence we get the 5/2 in these expressions. And by the same argument, we get a constant volume heat capacity of 5/2 nR, and which again here on the slide is written in both that molar and molecular form. And I just did that here to cover our basis so that if you have a problem that for some reason decides to give you information about the number of molecules as opposed to the number of moles, you can pick the correct expression. K, of course, is that the 1.38 times 10 to the minus 23 joules per Kelvin. I had to think for a second, like, what's the units? Hopefully we all remember that, right? No, I had trouble there. And R was the ideal gas constant. So again, a lot of information here. Notice that C sub V, the constant volume heat capacity, appears in a number of places in this table. There's actually also a thing here, C sub P, which is the constant pressure heat capacity, which I just stated in the isobaric, because it turns out the isobaric process can be looked at as the defining case for constant pressure heat capacity, and that is defined in text out there, but you don't need to use that because this expression here just references these constant volume heat capacities that we've already been provided with. So with those, you can, depending on what you're asked for, you can probably look up the right formula in here to use. Now, maybe let me say a few words about each of these formulas and what each of the processes is about. So isochoric, which there are sometimes, if you look in different sources, you might occasionally see some different names. Like I think isovolumetric is one that I've run into, but I prefer to say isochoric. Basically means constant volume, and that explains why there's a 0 entry here in the work column, because when you're at constant volume, a gas can't really do work to its environment at all, because if it's a constant volume, it doesn't expand or contract any. That means no displacement. You need force times displacement to do work. And the formula for the heat really is just following what we just talked about, the definition, you could say, of the constant volume heat capacity of a gas. Isobaric means constant pressure. And when pressure is constant, it turns out the work done by that system, normally we'd say force times displacement if force is constant, right? But if we said, oh, well, let's take displacement and multiply that by area and then interpret that as volume and then take that force and divide by area, that then would be a pressure. So this pressure times change in volume is just a expression for work done by a constant force when that force is actually related to a pressure force, and the work that's being done is because there is a gas that is changing its volume. Maybe it's expanding, as we've, I think, seen in one example already. The heat formula here in this particular situation, to actually get to this, requires, I think, an argument involving the ideal gas law. So maybe this is the point where I start stumbling a little bit, because in this class, it is not really my intent to derive every single one of these formulas or tell you exactly where all of them come from. This one we could probably do, but it turns out the next 3 down here, really, I think this 0 I can explain, but these other ones are all pretty calculus based. So the perspective we're taking in this class is you have formulas, you can look them up. And that is okay in science, because even if you know all the math that leads to a formula, there are plenty of situations, real applications, whether you're doing research or just using the results of science in some other application. There are a lot of situations where you have a formula, and the main thing is to know what it means, and then based on that, be able to figure out how do you put quantities into that formula and get a desired result and usually that desired result comes from an interpretation of some question that's stated in words. And I think that's the way I'd like to look at this table, is all these formulas do that. So again, the isothermal means constant temperature, and at constant temperature, pressure and volume are inversely proportional to each other. And when it comes to doing things like calculating work, that's why things get a little bit difficult and why this natural law kind of pops into things. So that it turns out that's usually what one would derive there. What's amazing is these two formulas are equal, or is that really amazing? If if it's isothermal, and that means constant temperature, and if our argument is that when we're applying the first law of thermodynamics to a thermodynamic system, the internal energy really is the thermal energy, and therefore change in internal energy is the change in internal, or in change of thermal energy of the system, which kind of like what we already have stated up here. If that's the case, for an isothermal process, the system itself is not changing its energy, which means the work done by that system should just equal the amount of heat put into it. Hence, these two formulas are the same. So at least we can explain that. Again, getting to it is a little more calculus-based. The adiabatic process is perhaps the most complicated mathematically. It turns out to get to this formula goes even beyond just regular old everyday household calculus, but gets into the theory of differential equations. So this is definitely a formula that we're going to look at as like, here it is. We're going to learn how to do something with it. There's actually a new symbol in here that I haven't even introduced yet in this topic. It turns out the next topic focuses on the adiabatic process. I simply included it in this table because after you've gone through this topic and the next one, and maybe a few more after that, at some point you might like to have something that you can copy into your notes, and I think this table is really good, so I just wanted it here for completeness and to round out our understanding of what all these things mean. I mean, we've seen constant volume, constant pressure, constant temperature. Those are kind of the three dynamic variables in the ideal gas law. So why is there even a fourth process? Well, heat is kind of a variable we've defined. It turns out it's a little tricky. I don't want to call it a variable so much because heat isn't really like a function of the state of a system, which is usually when we call something a variable what that is. Heat is something we do to a system, and in that sense you can't really say like a system contains an amount of work. You can't really say a system contains an amount of heat, but nevertheless the fourth thermodynamic process is the one that corresponds to no heat, Q equals 0, which I think from a certain point of view you could say like constant volume is like delta V is equal to 0. Constant pressure is like delta P is equal to 0. Constant temperature is like delta T is equal to 0. And the last one is Q is equal to 0. So for each of these, we're setting something equal to 0. And then that defines the thermodynamic process for us. And this definition of what adiabatic means is really what gives us this zero entry. It turns out adiabatic processes are some of the most useful kinds of processes for modeling a wide range of real phenomena, particularly in describing what air does in various weather related types of phenomena.